Okay, hello there. This video is going to be a little bit about related rates, and I'm going to just be solving some problems and sort of talking through my my thought process here, my problem solving process. I'd encourage you to maybe watch a couple problems and then try some on your own. So I'll probably do more than I'm expecting you to watch, and that'll just give you more resources if you want to see some more problems being solved. All right, so let's get right into it. So here's our first problem. On mathy start with Harriet. So Harriet assumes x and y are differentiable functions of t. What does this mean? Well, what this means is that as time changes, so does x and y. So they may be related in some way, x and y, but also as time changes, these values are changing. So in general, what we might think about is some sort of relation or curve, and something is moving along the curve. And we're going to talk about this more when we talk about parametric equations, which is basically very similar to what this is right here. But imagine that instead of just having a static relationship, here's a curve, we have something moving along the curve. So as time is passing, both the x and the y values are moving, but they're also related by this curve. She decides she wants to find dx dt when x equals 3 and dy dt equals 2. And she has this relationship x squared y cubed equals 9. Let's help her out. Okay, so when you're solving related rates problems, I think some of the good things to do are to write down what you know. So what we know is at this specific point, we know that x equals 3. We know that dy dt equals 2. And we want to know what dx dt is. Okay, we haven't explicitly been given y, but we may be able to find it. Okay, so we were given x, we were given dy dt at a specific time, right? This doesn't mean that it's always 3. It just means we're curious about that one point, and that's really important. And then we're asked to find dx dt. So we wrote down some stuff that we know. I think this is incredibly valuable, writing down what you know and what you want to know. You also need some sort of relationship to relate the two things that are changing with respect to time. Well, in this case, we were just given this relationship, which is x squared y cubed equals 9. This is a static equation. Nothing's changing here, but it relates x and y. Once you have those things, what you really want to do is differentiate both sides with respect to time, because again, we are dealing with a rate of change with respect to time, dy dt and dx dt. So we're going to do that. We're going to take ddt of this side, and we're going to take ddt of this side. If these things are equal, then their rates of change with respect to time should also be equal. We're going to need the product rule on the left-hand side. So we're going to take the derivative of x squared, which is 2x times dx dt. That's the chain rule, because remember, we're not just taking the derivative with respect to x, in which case we'd multiply by dx, which is just 1. We're taking the derivative with respect to time. And so x is a function of time. Therefore, we need to use the chain rule and multiply by its derivative. So that's the derivative of the first times the second plus the first times the derivative of the second, which would be 3y squared. That's the derivative of y cubed with respect to y, but then we need to multiply by dy dt. That is the chain rule. And then that should equal 0. The derivative of 9 with respect to time is 0. 9 is not changing even as time passes. So that's the calculus, right? Taking that derivative with respect to time, making sure we use the chain rule, and in this case, the product rule. So we're looking for dx dt, so we don't need that. We have x and we have dy dt, but in order to solve for dx dt, we also need y. So often you have to go to your original equation and figure out what something is at this point in time. So since we know that x is 3, we should be able to find y. So I'm going to plug in 3 for x and get 9y cubed is equal to 9. That means that y cubed is equal to 1. So y equals 1. So I can fill that in over here at this specific point in time. Something's moving along this curve. Just at that point, y is 1 and x is 3. Now I can basically plug everything in and solve for what I want. So since x is 3, I can plug that in. So I'm plugging things in from this equation now. I should get 6 times dx dt times y cubed, which is 1, plus x squared, which is 9, times 3 times 1 times dy dt, which is 2, equals 0. Now I've got 6 dx dt plus 18 times 3, which is 30 plus 24, or 54, equals 0. And so if I solve that for dx dt, I should get dx dt is equal to 54 divided by 6, which is 9. Yep. -9. So basically what this tells us is that when dy dt is changing at a rate of 2 units per let's say, second, dx dt is changing at -9. Now let's look at what this would look like graphically. So I'm going to pull up a graph on Desmos. X squared y cubed equals 9. So go to my mouse, come here, let's go to desmos.com. Okay, let's clear all these drawings, go to the graphing calculator, and let's type in x squared y cubed equals 9. Okay, so the point we're interested in was this one right here, right? That's the point 3, 1. And basically what we're saying is, if the y value is increasing at 2, we must be moving this direction, right? Because the y value is increasing. And so it makes sense that if it's increasing at 2 units, that x should be decreasing because x is getting smaller. So we're basically saying, hey, since y is increasing by 2, it's going up, the x value needs to be decreasing, and actually decreasing faster, because you can see that x is changing here more quickly than y, right? Because it's a little not very steep. Okay. Hopefully you saw that Desmos graph. I really hope so. All right, so moving back to this. We've sort of learned 2 things. One, write down what you know, make sure you have an equation, differentiate with respect to time, possibly use the original equation to find something if you need an additional variable, and then plug things in and solve. So let us take a look at Griffin's hot air balloon truancy and see if we can apply some of these same strategies. So Griffin decides to skip school in order to go for a hot air balloon ride. He rises straight up from a level field in her balloon. Uh-oh. Looks like I need to edit this. His balloon, and is tracked by a rangefinder 500 feet from the liftoff point. At the moment, the rangefinder's elevation angle is pi force. The angle is increasing at the rate of 0.14 radians per minute. How fast is Griffin rising at that instant? Okay, a lot of stuff there. An additional thing that can be really, really helpful when solving these problems is to draw a picture. So let's go ahead and draw a picture first and see if we can get a sense for what we're dealing with. So let's see here, straight up in his balloon. So here's our balloon, right? It's got a basket under here. Griffin's floating up in this balloon, and straight up from a level field. So here's our level field and the balloon going up. Now there's a range finder, which is 500 feet. And I can label this 500 feet because it is, in fact, not changing, right? This distance, the rangefinder from the liftoff point, is not changing. So I can just label that. Okay. And then it says the moment the rangefinder's elevation angle is pi force, it's increasing at a certain amount. So it looks like this rangefinder is looking up at the balloon, and we have some sort of angle in here. So I'm going to call that theta because it's changing. It's a variable. Now, it's true that they want to know right when it's pi fourths, but it's not always pi-4ths. It's often changing. Okay, and so that's theta. And then it wants to know how fast Griffin is rising at that instant. So basically, they want to know how quickly this is changing over here. So a good thing to do is to think about, if I'm going to draw my picture, let me put variables on things that are changing. Okay, so I've got theta here because that's changing. I've got y here because that's changing. I can put 500 because it's not changing. Okay, so we've got a good picture. Now let's write down some things we know. First of all, we know that we want to know dy dt, right? How fast is Griffin rising at that moment would be the rate of change of y with respect to time. We know d theta dt. D theta dt is 0.14. We also know at this instant that theta is pi-4ths. Okay, so these are some of the things we know. And now we need an equation to relate these two variables. We need a static equation to relate these two variables. So if we can get a static equation to relate these two variables, then we'll be able to take the derivative with respect to time and plug in what we know. So a good equation to relate these two would be tangent of theta is equal to y over 500. Alternatively, we could write 500 times tangent of theta is equal to y. So we've got our equation, we've got the things we know, we've got a good picture where variables are labeling the things that are changing, and now we can take the derivative with respect to time. So let's do that. The derivative of this side with respect to time, d dt of 500 tangent squared theta equals d dt of y. So the derivative of this side would be 500 secant squared theta, but then we'll multiply by d theta dt because we are using the chain rule and we're taking the derivative with respect to time, not theta, and that should equal dy dt. Okay, so we want to know dy dt. We have d theta dt and theta, so at that point, we should be able to figure some things out. Now, let's see if we can not plug in theta and think about what secant would be. Remember, secant is 1 over cosine. So if this is 500 feet and this is pi-4ths, this is also going to have to be 500 feet, right? Because it's a pi-4ths triangle. And so that means the hypotenuse, let's just call it h for the sake of it, is going to have to be 500 root 2. Right? Yeah. So that means that secant theta, right, cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent would be 500 root 2. That's hypotenuse over adjacent, which is 500. So that's simply square root 2. That's secant theta. So secant theta squared would just be 2. Secant squared theta of pi-4ths is simply 2. So I can replace secant squared with 2. So I've got 500 times 2 times 0.14 equals dy dt. And then I can use my calculator to find that value, or I could do it in my head probably. 1,000 times 0.14 should be, I think, 140 feet per minute. I was gonna say feet per second, that'd be real fast. 140 feet per minute, still, still moving up at a decent rate. So that's how fast Griffin is rising at that instant. So again, let's review briefly what we have here. And what we have here is we drew a picture, we labeled some variables, things that are changing. We wrote down what we knew. We wrote an equation to relate the variables that are changing. And then we took the derivative with respect to time and plugged some things in. Not a particularly easy type of problem, but a lot of fun and quite practical. I mean, I think we're all probably going to do this in our, basic lives moving forward. Okay, how about filling Veronica's conical tank? So water runs into Veronica's prized conical tank at the rate of 9 cubic feet per minute. The tank stands point down and has a height of 10 feet and a base radius of 5. How fast is the water level rising in Veronica's tank when the water is 6 feet deep? So again, we're going to start by trying to draw a picture here. And then from there, we will see what we can do. So we've got a conical tank. Whoops, my pen's upside down. That stands point down. Okay, so it looks something like this. And water is flowing into this tank at 9 cubic feet per minute. Now we know that this conical tank right here has a height of 10 feet. That's not changing. And a radius of 5 feet. Now, this is actually a really important piece of information because that ratio is going to remain true throughout the entire, the entire cone. And then we've got some water down here, right? And things are changing. We've got the height of the water, which is changing, and the radius of the water will be changing as well. Okay, so let's see. Let's write down a few things we know. So first of all, we know that water is flowing in at 9 cubic feet per minute. That is dV dt, right? That's how quickly the volume is changing, and that is 9. How fast is the water level rising? So that is dH dt, and we want to know what it is. What is dH dt? Now we know at this specific point that it's 6 feet deep. That means H is 6 at this specific instant. So here are some of the things that we know, and we're writing them down. Okay. Now we need some sort of an equation to relate V and H. Well, what I know is that the volume of a cone is actually 1/3 pi r squared times H. So that relates H and R and V, which is fine, but I would prefer if it just related V and H. So I'm wondering if there's some way to relate R and H and do some substitution. So this is where it comes into play, where you know that, okay, if this whole tank has a height of 10 and a radius of 5, then that means the relationship between H and R, that R has to be 1/2 of H, right? No matter where you are in this cone, the dimensions don't change. So, or the ratio of the dimensions don't change. So R should be 1/2 of H, and that's always true. So we can actually plug that in here and get V is equal to 1/3 pi times R squared, but we're going to write H squared over 4 times H, right? We basically took this 1/2 H and plugged it in for R. Okay, so that gives us the equation. V is equal to 1/3 pi times H cubed over 4, or V equals 1/12 pi times H cubed. That's great. So we have a nice picture that helped us out. We've got some information. We've written an equation that just relates the two variables, which is really helpful instead of having that additional R. Okay. This is kind of all the hard work. And now we're going to get to the calculus. I'm going to erase some things so I can write over here. But basically now we need to take the derivative with respect to time. Taking the derivative with respect to time, we should get that dV dt is equal to pi over 12, that's a constant, times 3h squared times dH dt, right? This is the derivative of h cubed with respect to h. That would be 3h squared, but then we have to multiply by dH dt using the chain rule. Now we just need to see if we have everything we need. We want dH dt, so that's fine. We have h, we know what pi 12ths is, and we have dV dt. So then we can say 9 is equal to pi over 4, because pi over 4 is pi 12ths times 3, 6 squared times dH dt. 36 divided by 4 is 9, so we get 9 equals pi times 9 dH dt. Dividing, we should get that 1 over pi is equal to dH dt. And so the height should be increasing at a rate of 1/pi feet per minute. Okay, not the neatest thing, but I kind of ran out of space here. So that's what I would do. So again, we drew a picture, we labeled some variables, we thought about the relationship, we wrote down what we knew, we found an equation to relate the two variables that are changing. And then we took a derivative with respect to time and plugged some things in. Okay, I'm gonna leave these two. Anya switches sports. Baseball diamond is a square with 90-foot sides. Anya hits the ball, runs towards first base with a speed of 24 feet per second. But you could draw this out, try and find a relationship between the variables. And the same thing here with Philly's parabolic run, which is similar to our mathy start with Harriet. You can think about, okay, where is he? Can I take the derivative of this with respect to time, etc. Very similar. So you can give those a try if you want. And I will see you soon. Sounds good.